Sorry, there we go. Um, Fixing. Swear, it's fixed. I have a cat in my lap. There he is. He doesn't want to get down, but I have to get him down now. So just everyone say hi to Stuart. He does not like me doing that, and now he's jumped down on his own. All right. Um. Okay. So with that, today we're going to be jumping into talking about searching and sorting. So that's the topic today: searching and sorting. Um, just as a reminder, the exam is Friday. We'll have more about the exam during the exam review Wednesday. You would eat. Okay, yeah. Let's. Thank you for letting me know that. That's not even needing. Give me 1 second here. Sorry, I'm having issues here. Okay. Can't actually close the timeout window. There we go. Sorry, had to ban someone. All right. No one's eating my kitties. Anyway, with that, exam review on Wednesday. The way I'm going to do this is similar to how I would normally do it in class. It's going to generally be open questions. Expect me to post on Piazza an open thread where people can just post questions that I will then try to address on the exam review on Wednesday. Certainly, I'll take live questions, but it's easier for me given the online format if I have some kind of prep in advance. We should get a list of topics up soon. We don't have it up just yet, but certainly given kind of how long the month of March has been, with everything that's happened, we want to make sure that everyone knows what topics are on the exam. I'm not going to answer too many exam questions today, just because we do have a lot to get to. Homework 4 is due Wednesday. A big problem I've been seeing: this homework has a 4 megabyte limit. Um, Will the next exam focus on new material? So if you're talking about the final exam, because that's the only exam left, the final exam will be cumulative, but it will mostly focus on material after exam 2. Exam 2 is not strictly cumulative, but if you're not comfortable with like things we covered from the first exam in Java, you will presumably struggle. Um, One of the big problems I've been seeing is pictures are too big, and I don't have word wrap on, so that's gonna. There we go. If your pictures are too big, you're going to go over the 4 megabyte size limit. So you need to decrease the size of your pictures. Does exam 2 include today's lesson? Yes, it does. Um, this is the last new material on exam 2. Correct. So if you're seeing that excess size limit, we cannot increase it. You have to decrease the pictures. Where do we keep the screenshot of the GUI? You can put it in any folder. You can put it in the root folder. You can put it in the images. Anywhere is fine. That's just so that way that we know that you at least got it working. Because then if we have issues, we can do it. Does open question mean open note? So we're by I'm talking about the exam review when I mean open questions. We're going to talk about the exam procedure more specifically on Wednesday. I'm going to highlight some key points today, but I will not take questions on it just because we have kind of too much to get to today as it is. So first, um, these are basically the announcements. Homework 4, submit on WebCat. You have to make your images and everything combined smaller than 4 megabytes. Will it work if we zip the pictures? Absolutely. Um, Although keep in mind that zipping the picture separate from zipping the overall file won't actually save space. Um, Not generally, anyway. So the exam will be asynchronous. It will be open note, open internet, open IDE. I want to be clear on why we're doing this. It's because this is an online course. We cannot monitor people taking the exam. All we can do is write our questions in such a way that just copying and pasting from slides won't work. Uh, we are writing the code in such a way that you will not simply be able to copy and paste it into your IDE. So you will have those features available to you. OpenNote, Open Internet. It is not open each other. And if we find any cases of cheating, I want to be very clear. You will get an F or a no credit in the course. If we find that you cheat on the exam. By that I mean we will be comparing test answers. There will be a lot of open-ended type questions to try to maximize the chance that we catch cheating. So do be aware of that. Open-ended, by the way, includes coding. We don't intend to make the exam harder than exam. Is the exam timed? Yes, it will be. So it will be asynchronous, but you will still have 50 minutes. That means to say, when you open the exam, you have 50 minutes to complete it. I would not recommend doing the exam anywhere other than a place with very stable internet. Because if your Wi-Fi cuts out or something like that, we can't help you. So do be careful with where you're doing the exam. Make sure you have a stable internet connection, etc. Because we just have to treat this as best as we can, given that the exam is remote. But that said, yes. Does this mean no stream Friday? There will not be a lecture on Friday, correct? Further, because the exam is asynchronous, so again, how does it work with different time zones? You will start when you want to. We will open up a period. Something like, these are not the times, don't write them down, but it will be something like the exam will be open from 9 a.m. to 9 p.m. Eastern, at which point you can take the exam in any period during that time. If you sleep for 12 hours, then you're going to have to wake up early to take the exam or go to bed late. Take your pick. But a 12-hour, it won't necessarily be a 12-hour window, but it'll be something like that. Say 9 a.m. to 9 p.m. At which point, once you start, you have 50 minutes. Because this exam is asynchronous, we will not be able to answer questions on exam day. If something is written incorrectly or something is misleading, we will address it later. For example, on exam 1, we threw a question out and gave everyone full credit because there was a typo. You would expect to see something like that rather than answering questions, because it wouldn't be fair if we answer a question at noon for people who finished the exam earlier. So I'll have more on that on Wednesday. I'm not going to spend the rest of this lecture answering questions about the exam, but I just wanted you to be aware of it. There will still be a quiz this weekend. I know, groan, F in chat, but we do want to make sure that this material that we're teaching sticks. This will be separate from the exam. Just briefly, these are the topics we have covered so far. And I'm just going to give you a chance to just look at this. I'm not answering questions about it right now, but these are the things that you can expect to be on the exam. All right, moving on. And this is, by the way, all the material we've covered since exam 1. So, last time on Friday, we talked about complexity classes. Constant time, log. Is this the topic list? Will be on Colab. It should be more detailed on Colab. We'll get one up at some point. Today, tomorrow, Wednesday, probably today or tomorrow, I would hope. So we talked about these complexity groups: constant time, logarithmic time, linear time, log linear time, quadratic, cubic time, and exponential time. From there, with these complexity groups, we broke down how much worse exponential time is, but I also did a demonstration, if you remember, with my sorting example, and don't worry too much about the exact code, but I compared something called a selection sort, which we'll talk about today, to something called a merge sort, which we actually won't get to today. And I showed how the selection sort would take literally hours to do a sorting problem of size like 10 million elements, whereas for a merge sort that took seconds. And the point being, these algorithmic complexity groups are really different. Log linear time is substantially better than quadratic time. Pardon me. So, from there, another perspective is, let's say you had 1 day to solve a problem, and you had an algorithm that was size log n. What's the largest number of elements you could have in your input size that a log n problem could solve? And assuming you could do 1 million steps per second. And the result would be an insanely big number. In fact, even if it were a linear time algorithm, you'd be looking at being able to do 84 billion size input, and you'd be able to iterate over them all in a day, provided you could do everything a million times a second. By comparison, if you look at something n factorial like Naive, traveling salesperson we talked about last time, if I gave you a century, you could only solve a Naive traveling salesperson of size 17. And any more, you need more than a century to do that. So exponential's pretty bad, is kind of the point here. Anyway, now we're going to talk about applications of this. Specifically, we're going to talk about searching and sorting. So the first example, searching, is we are looking for some value, and we are trying to determine whether or not that value is in a list, and if so, where in the list it is. And we're describing this at an abstract level, so we'll talk about this from a standpoint of a list of integers, but that is, or an array of integers. But that said, this abstracts to any list and any type of element, not just integers. From there, we're going to also look at sorting. So rearrange them, and I don't know why I wrote this as non-decreasing. I could just say ascending order. That's fine too. So from here, we're going to first talk about searching algorithms. So I personally am not a Harry Potter fan. The person who wrote these slides used it, and I didn't feel like changing it. So let's say someone told you, open your textbook to page 394. How are you going to find that? Are you going to, let me grab a book here. Let's see. Oops, my web camera just fell out. Are you going to look? So by the way, this is House of Change by Steven Erikson. Great part of the Malazan Book of the Fallen series, if you're looking for some fantasy reading. If you think Game of Thrones is too simple and has too few characters, you'll like Malazan Book of the Fallen. Anyway, how are you going to find page 394? Are you going to go page 1? Nope, that's not it. No, 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 that's not. No one's going to search through a book that way. What you'll do is you'll open, and I'll say, okay, I'm on page 538, so I need to go to the left. And now I go about halfway, and I say, okay, now I'm on page 285, and I go to the right. And the point is, you kind of hone in that way. You search, break the search space in half, go to the side. And we did an example of that last time. Remember the guess a number game? If I said guess a number 1 to 100, and I told you higher or lower, you would look at first 50 in order to cut the search space in half. Those are two different sorting techniques. A sequential search or a linear search is this process. So I search, is this it? No. Next page, no. Next page, no. Next page, no. That is a sequential search, and it's fairly simple to write. You could write this simply as, and I'm going to write a function here, private static int linear search. Sorry, thought I was typing Python for a second. This takes in an int array and an int target. That is the target being the value that we're looking for. And from there, we're going to return the index that target is found in the array. And this is a fairly straightforward process. For int I equals 0, I less than array.length, I plus plus if array I equals target, then return I, that is the index where the value is stored. And if we get through the entire for loop, having never found it, that means the value isn't there, at which point we'll return something called a sentinel value. And the reason that we return -1 is -1 is not an index that exists in the array. Are we going to talk about insertion sorts? Yes. It is not an index in the array. So -1, if I were to call this function and it returns -1, that tells me target not found. Otherwise, any other index I get is where the value is stored. This is a linear search, and it's fairly straightforward. That's fine. Okay. Now, obviously, that may not be the best way to search, as I showed with this book example. So from there, going back to the slides, the thing with the linear search is this. If the item is present, in a best case scenario, we talked about this analysis of algorithms, if my list is size n, a best case scenario is that the first element of the list is the item I'm looking for, which is to say it takes 1 step or constant time. But in a worst case, it takes n steps. It's the last element in the array, at which point I have to iterate over the whole thing, or I have to do n steps. And as a result, on average, this takes half of n. Now, as we talked about last time, when we're talking about asymptotic analysis, we want to look at the complexity class. So when we say that something takes n over 2 steps, that means the steps are proportional to n, or this is O of n. That is, as n increases, I can expect the number of steps to increase. So in a average case, this is still O of n. Now, generally, when we do asymptotic analysis, we are actually really only interested in the worst case. There are exceptions to this when we get to amortized analysis, but generally we're going to look at things from a worst case perspective. And in a worst case, this is n steps. From there, if the item is not present, no matter how we wrote this, looping through all the values to determine whether or not it's there. If it's not there, we're going to have to complete this loop. This loop is therefore going to take n steps plus 1 for return, or n plus 1. Now again, we're not really interested in the plus 1, so if the item value is not there, it is also n steps. So should it be that? The reason it's not that is because I am using less than array.length. If I used less than or equal to, then I would need to do -1. But because I just use less than, when I equals the array length, this loop will not proceed. So that is a sequential search. Now, let's consider a binary search. And for a binary search, and I'm going to need to fix my whiteboard camera because Stuart knocked it over when he was getting down. Give me 1 second to do that. Okay, there we go. So with a binary search, what we're going to do is, let's say I have an array. Let's say this is for now size 7. So, size 7. And let's say my numbers are 8, 12, 19, 24, 32, 54, and 71. Please let me know, by the way, if this is not clear. Hang on. Does binary search return the index at which the number is found? Yes, linear search does as well. So from there, what we're going to do is we're going to define our middle. Let's say I'm hypothetically looking for the number 19. This is my target. I am then going to say I am looking for 19 between 0, index 0, and index 7. I'm going to look between these two numbers. So the lowest index my value can be at is 0, because it could be here. And the highest index okay, sorry, I'm just making sure that wasn't a question for me. And the highest index value could be is, sorry, that you're correct. This should be 6. Yes, thank you. The highest value could be at is 6. So it's between 0 and 6. It's bounded on the low side and the high side. If my value is in this array, clearly it is at index greater than or equal to low and less than or equal to high. Correct. So from there, I'm going to define my midpoint. And my mid is going to be equal to low plus high divided by 2. And I'm actually going to stipulate that we're just going to round this down. That is to say that we're going to cast this to an integer. And while this may not be relevant here, because we don't need to, if this sum were odd, we would. So for now, low plus high is 6. 6 divided by 2 equals 3. So now I'm going to look at index 3, and I'm going to say, hey, is this 19? Well, is it? No, it's not 19. So rather than stop here, I'm going to say, okay, so if this value is not 19, I'm then going to say, is 19 greater than or less than this value? And because 19 is less than 24, I'm going to ignore this value as well as every value to the right. That is, 19 can't be here, and it can't be to the right of this. A binary sort rounds down. Yes, a binary search, not a binary sort. We're not sorting, we're searching here. But yes, a binary search rounds down. By the way, it doesn't actually matter. You just have to write the code a little bit different. Okay. So from there, I'm going to change my values. Now, my low is still 0, but my high is no longer 6. My high is whatever my mid was minus 1. That is to say, this is going to be my high now. So I'm going to change the value of high to 2. I'm then going to rerun this loop. I'm going to get the mid. Mid is equal now to 1, because it's 0 plus 2 is 2. Divide by 2 is 1. I'm now going to look at index 1. And index 1 is 12. Is 12 my target? No. My target is 19. It's greater than 12. So I now need to look to the right of the mid. So I'm going to ignore the mid and the values to the left of it. And now my low value changes to be mid plus 1. Or 1 plus 1, 2. Now my low is 2 and my high is 2. 2 plus 2 is 4. Divide by 2 equals 2. So now I look at index 2. And hey, look, I found my target. These two values are equal. And because these two values are equal, I simply return mid. I return this value. Now, what would happen? The question is, what if instead of this being 19, what if this value were 17? So now, obviously, I haven't found 19 yet, correct? So if I were to keep searching, and I apologize for the glare that's kind of right there. I can't really fix that. So now if I were to be looking for 19, I would say, well, okay, 17 is less than 19, so we can't consider that. So let's look at the values to the right of it, which is to say that low equals mid plus 1, same as we did before. When we look to the right, we set low to mid plus 1. When we look to the left, we set low, or high, excuse me, to mid minus 1. So now I have a problem, though, because my low is 3 and my high is 2. This is problematic because generally we want to make sure that low is less than or equal to high. But it's not. This is false. And so at this point, we know that our value is not in this array. So we return -1, our sentinel value for not found. So building off that, let's now actually return -1, meaning not found. Is the same thing as a binary search tree? No, a binary search tree is a data structure. A binary search tree bases itself on the ideas of a binary search. You search through it like we just did, but a binary search tree is a data structure, not an algorithm. All right, so now let's actually try to write this. Let's try to write private, make this public static int binary search. This is going to take in an integer array. This is also going to take in a target. Now, some of you may be familiar with recursion, and this may be your intention to write it this way. We're not going to talk about recursion yet. That's later on in the course. So we're going to do this in an iterative way. The first thing I'm going to do is I'm going to say my int low equals 0, and my int high equals, in this case, array.length -1. That is to say, the last value in my array. And then I'm going to remember what our exit condition. When did we stop looping? We stopped looping either when we found the value or while we continued looping, I should say, while low was less than or equal to high. And just to be consistent, I'm going to change this to high with two letters. From here, each time through the loop, we calculate mid equals low plus high divided by 2. And by default, this rounds down because Java truncates any decimal place. From there, if array mid equals target, this means that we found our target, so we return mid. Index target is stored at. Else, there are two possibilities. Else, if array mid is greater than the target, that is to say the target, or you could say target less than array mid, either way. At this point, how would you work with a binary search to work with other data types? You would change the equals to dot equals, and you would change what I'm doing here to a dot compare to method or a dot compares method. But for now, continuing on this stream, this would be look left. That is to say that if the target is less than the mid, we want to look to the left. How do we look to the left? We say high equals mid minus 1. Yes, high, low, and mid are the index positions, not the values. Correct. They are the index or indices. So these two values are index of high and index of low, and mid is the index of mid. So array mid gives me the value stored at mid. At this point, I just say high equals mid minus 1, and I allow the loop to proceed again. Else, the only possibility left, index, target, else we need to look right. That's because the mid, we already know the mid is not the target, and so there's no reason to check the mid again. So we're going to check to the left of mid, and so as I demonstrated on the whiteboard, if this were our mid value and we know our targets... That was my chair. Sorry about that. Let's see here. Sorry about that. So I look at the mid. I'm looking for, say, 19. That means I know the values to the left. So I'm not going to bother looking at the mid again, and I'm not going to bother looking at anything to the right. And so now what I want my low and my high to be, retrospectively, is low to high. And the high index is whatever my mid was previously minus 1, immediately to the left of mid. Isn't target the value... Oh, yeah, sorry. Isn't the target value correct? Sorry, I'm trying not to knock my camera over again. There we go. Sorry about that. All right. So now, else we're going to look to the right. And if we're looking to the right, that means we're going to say low equals mid plus 1. Now, what happens if we exit this loop? If we exit this loop, this means that low must be greater than high. That means that we have exhausted every possible option, searching through our list, or searching through our array in a binary way. That means it's not there. We return -1. Again, this means not found, a sentinel value. Now, let's take a minute and analyze these two algorithms. This algorithm is trivially, very trivially, this is O of n, because we potentially look at every value. But what about this? Well, this is where it gets a bit tricky. You have to do some analysis, and it would involve, if we really wanted to get into it, some calculus too. So instead, I'm going to wave my hand magically and say, this is O of log base 2 of n. That is to say, the number of elements we need to look at is the ceiling of the log of n. The advantage here is if I have 1,000,000 elements, it only takes 20 steps to look for my value. Whereas in the case of linear search, it would be 1,000,000 steps potentially. On average, 500,000 steps if you know the value's there. So with that, excuse me. This is the idea of the binary search. This is how we do that. And I'll leave this code up for a second. I'm not expecting you really to memorize it, but you should be able to recreate it just by thinking about the problem. Again, to do this for not integers, if these were objects, we would just say use dot equals here and dot compare to here. And we've talked about compare to and comparator, so you can go back and look at that material if you need to. Any questions, or does anyone see any potential bugs here? I think I wrote this correctly. If a list... Pudge got it, because I was about to say, why don't we always do a binary search? There's an assumption baked into a binary search that I haven't touched on yet. And the assumption is that the list is sorted. A linear search does not require the list to be sorted. Here it is. It doesn't matter if the list is sorted or not. We have written a linear search or a sequential search. A binary search relies on the array or the list already being sorted. And if it is not, then the binary search will produce incorrect results. For example, please don't knock the camera over this time. For example, Would this be used on a tree set? Trees don't have orders. You can't search. Will this code be posted? Yes. Trees don't have order, or excuse me, I should say sets don't have order, so you don't really search a set the same way that you search a tree. Searching on a set is always actually constant time because it relies on hashing in the case of a hash set. In the case of a tree set, it's log n and it works in a similar fashion, but it uses the binary search tree, which we haven't gotten to, so I'm not going to discuss that just yet. Let's say this were my array. Sorry, that should be 34. If this were my array and I tried to do a binary search for 19, my mid would be here, and I would say 24, well, that's greater than 19, so let's only look to the left. Except notice, I just crossed out 19 right here. This should have been what I returned, index 4. Instead, I've already ignored index 4, and the reason I did this is because this is not sorted. So if the underlying array is not sorted, a binary search does not work. Can you implement binary search recursively? Yes, but we haven't talked about recursion in the class yet, so I don't want to introduce two concepts in one day. But yes, you could absolutely. In fact, normally, I would say you would do this recursively, but just for the sake of keeping this approachable, I focused on using a while loop. Any other questions? So you have to sort an array before passing it to a binary search. If you want the results to be correct, yes. If the array is not sorted, you cannot assume the results of a binary search are correct. But this is why I can do a binary search for a page number in a book, because the pages are in order. Or I could do a binary search on a dictionary, because the things are in order. Why not search the right side as well? Because with a binary search, the entire point is I'm trying to reduce how much I'm searching. I wouldn't search the right side in a binary search because I would be making the assumption on this right side that everything to the right of 24 is greater than 24. So if we had an array of length 3, the middle would also, yes, the middle would be index 3, at which point you'd be dividing it into an array of size 3 and an array of size 4. So you don't divide it perfectly in half, but that's good enough for us to still say log of n. Yeah. So the reason you don't search the right side is if you were searching the entire array, you'd already be talking a sequential search. So we always go with the smaller index for the middle. Correct, except you could do that. You could round up and the algorithm would be just as efficient. What happens if there's more than one target number? If there's more than one target number, you would do separate searches. You do one search for one number and one search for another. And then it would still be 2 times log base 2 of n as opposed to 2n for sequential. So you would just do separate searches. You don't try to do multiple searches in one algorithm. Just write a single search algorithm and call it multiple times. All right, I'm actually way running late, so I apologize. Let me speed this up considerably, and if there are more questions, I'll come back to it at the end. So now, let's talk about sorting. So the idea of sorting is I have a group of information, and I want to sort it in a way that the items are in ascending order. So, for example, I could do a binary search. Let's say I needed to search for dozens of words. Let's say if you're spell checking a document, something you would often want to do is check, are these words in the dictionary? What if the list has multiple indices of the target value? You find one of them. So generally, with searching, you're happy if you find any one instance. Again, no more questions about searching for now. I'll just breeze past them and ignore them until I get to the end of lecture, just because I do have to get through sorting today. So now, we have insertion sort, selection sort, bubble sort. These are sorts, and we actually specifically have already looked at selection sort. They're pretty easy to explain. I'll show them off, but these are O of n squared, which means they're bad. They're really bad. Eventually, once we get to it, we will look at merge sort, but merge sort requires us to spend some time explaining recursion, which is something we're doing after exam 2. How many people here want recursion on exam 2? No one? Okay, great. So then we'll just put off talking about merge sort until after we've introduced recursion. But briefly, I want to show off a couple of these sorts. The first one I want to look at is a selection sort. And I should note the collections.sort uses merge sort. So collections.sort, you can assume, is incredibly efficient. Oh, everyone, sorry. We have to put recursion on exam 2. I'm subbed, wants me to put recursion on exam 2. So best of luck. Obviously joking. Anyway, so with that, I'm going to first start off by showing a selection sort. The selection sort is pretty easy to illustrate. Give me numbers between 1 and 20 for the sake of simplicity with no repeats in order, and I will write them down. Not in order, I should say. Very, very clearly not in order. I'm going to do an array of size 6, and I'm just going to look at the screen. I'm just going to write down numbers I see. I see not in order, he says again. Okay, I see some 3s, some 8s, some 1s. I saw a 4 and a 7. One more number. 9. No, let's get a smaller number than 7, because otherwise it won't be interesting. Let's go with 2. So the idea of a selection sort is this. I'm going to find the smallest value in the array, and I'm going to move it to the front. And so the way I do this, I go through this array, I loop through it, and by the way, the code is already there. It will be uploaded. I'm going to step through this array, and I'm going to find the minimum. The minimum is just, in this case, at index 2. And I'm going to say, okay, I want to move the value at index 2 to the front of my array, so I'm going to swap these two values. So 1 moves over here, 3 moves over here. 1 and 3. From here, I can now say definitively, everything to the left of this purple line is sorted. And you may be thinking, wow, that's great. One value is sorted. But now what I'm going to do is I'm going to look at the rest of the array, and I'm going to repeat this process. So now, starting at index 1, I want to find the smallest value left in this array. 8, 3, 4, 7, 2. 2 is the smallest. It's at index 5. I'm going to swap index 1 and 5. This becomes 2. This becomes 8. And now, coincidentally, I have the array already in order, so I'm going to cheat and say that actually I have 7 and 3 here. Not that I swapped them, but we'll just pretend the array was always like that. What kind of sort is this? This is selection. And it's easy to remember because you are repeatedly selecting the minimum and moving it to the front. So now everything to the left of this line is sorted. I now repeat this process. What's the smallest value from index 2 forward? It's at index 4. I swap index 2 and 4. This becomes 3. This becomes 7. I now say everything to the left of here is sorted. I then repeat this process, except 4 is already the smallest value. And then 7's already the smallest value. And I've completed the selection sort. The number of steps the selection sort takes. How many steps does it take to find the minimum of 6 values? Well, you have to do one comparison, 2, 3, 4, 5. So it takes 5 comparisons to find the minimum of the first value. To find the minimum of the next value over 5 elements, it takes 4 comparisons, then 3, then 2, then 1. That is to say that the number of steps of a selection sort is n plus ... 3 plus 2 plus 1. Or sorry, n minus 1 It turns out that the sum of this series is equal roughly to half of n squared, roughly. And so this is why this algorithm is O of n squared. And if you need a proof of that, take calculus 2. Wouldn't it be n plus n minus 1? Well, again, there is an implicit n minus, there's an implicit n minus 2 there after that. So n minus 1 plus n minus 2 plus n minus 3 dot 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 3 plus 2 plus 1, etc. So for big arrays, this gets slow. As we talked about, n squared, not great. Briefly, and I do have time, I'm going to now show off the insertion sort. And the insertion sort is a little bit different. With the insertion sort, rather than repeatedly finding the minimum, I'm going to insert each new value in the correct location. So let's do another array. I'm just going to make up numbers on the fly here. Let's do 17, 7, 14, 8, 3, and 20. If I want to do an insertion sort, I'm actually going to start with the assumption that everything to the left of this purple line is sorted. And from there, I'm going to insert 7 into the correct order in this sorted space. Now, I can already tell you that 7's not in the right place, correct? Because 7 should be less than 17, so I need to swap these. So I perform the swap, 7 and 17. But after I've done that, now there's no more to the left to look. 7's the smallest value. So now I assume everything to the left of this purple line is sorted. I've inserted 7 into the order. Is this insertion? Yes. This is insertion. From there, I need to insert 14 into sorted order. So 14 is less than 17, so they need to swap places. This becomes 14. This becomes 17. Then I check, does 14 need to swap with 7? And 14 does not need to swap with 7, because 14 is already greater than 7. So I'm done with this step. And now I assume everything up to index 2 is sorted. I then insert 8, the same way. So I'm going to swap 8 and 17. I'm then going to compare 8 to 14. It needs to swap. And then I'm going to compare 8 to 7. 8 is greater than 7, so we don't swap. Now everything up to here is sorted. 3 less than 17. 3 less than 14, so I swap again. 3 less than 8, swap again. 3 less than 7. And now there are no more values to compare 3 to, so we're done with that loop. Now everything up to here is sorted. Then finally we hit 20. We compare 20 to 17. 20 is not less than 17, so we do no swapping, and everything up to here is sorted, and we're done. Now the insertion sort, probabilistically, in a best case scenario, could actually be O of n, but in a worst case it's n squared, and so we treat it as though it were n squared. And that's the insertion sort. I don't have time to go through the bubble sort. What I will say is that this file here will be uploaded today. It includes every sort. So insertion sort, selection sort. I should note that this print array section, this is just if you want to see what the output looks like. There's directions for how to set this program up. The complexity of selection, insertion, and bubble sort is O of n squared. All three of them are n squared. The only one in this file that's not n squared is merge sort. But in order to discuss merge sort, we necessarily need to discuss recursion, and we haven't gotten that far yet. So for now, we're going to just say you're not expected to know merge sort, other than to know that merge sort is O of n times log n. You're not expected to know how it works. Can't any recursive function be done non-recursively? Yes, but it can be difficult. So for example, I can have a recursive function that draws trees, and I could implement that iteratively, but it's difficult, and it's a lot harder than you would think. Could you do the other ones with recursion as well? In theory, sure, but I would say it's a lot easier to do that. Are quicksort and heap sort also n log n? So quicksort's weird because quicksort is in a worst case O of n squared, but the worst case is astronomically rare to occur. So it's called a probabilistic algorithm, which is to say that it's typically experimentally O of n squared, but it has a potential, it's experimentally O n log n, but it's incredibly rare that it's n squared, but it is possible. It's just astronomically rare. You'd have to pick really bad pivots for that to happen. We're not going to talk about quicksort in this class. If I have time, I'll discuss it after we discuss merge sort, but I don't want to spend more of that. Again, anything you can do with recursion, you can technically do iteratively. It's just some things are a lot harder to do recursively than some things are a lot harder to do from a coding perspective iteratively than recursively. And if you're not going to get any kind of computational benefit from doing it iteratively, which in the case of merge sort you wouldn't, we just don't really bother because it turns out to be really hard to code, believe it or not. But yeah, quicksort and heap sort are also n log n. All right. Any questions? Is there a daily activity today? Well, let's check. So as always, go to Colab, and you will see under the assignment section if it loads. Fingers crossed. There is. Specifically, sorry, I'm on the wrong Colab. There's no homework 6 yet. I was on the wrong Colab. Don't worry, you didn't miss homework 5. There was no homework 6 yet. Sorry. There is a daily activity today. I was on my last semester's. Yeah, Monka S indeed. So here's the daily activity. There's also a lab today and tomorrow. And that's on algorithms. But the idea here, this daily activity, is you are going to, given an array, you're going to perform a binary search and say what index is returned, and then what is the sequence of indexes checked. So that is to say a comma-separated list. And again, the indexes, not the values. That's what we want. The indexes, not the values. Right, any other questions? And this includes questions on searching, not just sorting. At this point, I'm done presenting new material for the day. Everything else I'm going to do is just answering questions. And I will get this uploaded here in the next 10 minutes or so, this particular file. I just want to test and make sure my searches are correct first. Can you scroll to the bubble sort code? So I didn't go over bubble sort. Bubble sort is by far the easiest to code, but it's actually worse than every other sorting technique in terms of computational output. Yes, it's O of n squared, so technically it's the same as insertion selection, but in practical runtime, bubble sort's hilariously bad. One thing I will say before, what are the advantages of a disadvantage of a merge sort over insertion sort? So insertion sort's actually more efficient if your list is nearly sorted than a merge sort is. That's otherwise merge sort's better. I'll if I get time, I'll go into reasons for it. Now some of you may be thinking, Okay, that's great. Thank you for the animations on the whiteboard. Thank you for the code. But what I could really use, what would really help me understand these sorts, is if someone could show me the sorts, maybe through the form of, oh, I don't know, Central European folk dance. Well, if you are in that camp, first, kind of a weird thing, but whatever. Second, there is a group called the Algorithmics, and they do just that. So here are the Algorithmics. And to that end, if you want to see how a linear search is done as opposed to a binary search, you can see them through flamenco dance. Or you could look at an insert sort with Romanian folk dance. And it has music. Make sure the music is coming through here. It's not. Hang on. I can't open OBS. There we go. This is the Algorithmics. What is the sequence of indexes checked? We're just interested in the mid-index, so just the mid-indexes. In sour please, indeed. I'll drop a sour please in there. So now you are seeing, this is the insert step. So the people who are facing backwards are not in order. The people who are facing forwards are in order. And again, it's the Algorithmics. And there you go. And if you want to see how a merge sort works, you can see it through dance. So with that, I'm probably breaking some copyright rules here. So I'm just gonna go ahead and I mean, technically academic fair use, but I'll go ahead and link their YouTube channel here in chat real quick. There you go. For lab this week, it says, our algorithm should accept an array of comparables. Can you explain what that means? Yeah, so remember how when we've wanted to make our objects sortable, we have implemented the comparable interface? That means that we're sorting an object that's implemented, or a list of objects, or an array of objects, excuse me, that have implemented the comparable interface. That's all that means. Because remember, if something implements an interface, we can cast it to that type. And by the way, that link, that is for the Algorithmics. It's hard to spell Algorithmics. Any other questions? Off-topic question. After 1 p.m. After 1 p.m. Aw, Stewie's sleeping over on the couch. He was unhappy that Daddy kicked him out of his lap. He was in Daddy's lap all morning. Poor kitty. All right. Since Professor Bossett just went live with her section, if you want to see some of this material repeated, you can just go over to her section. Again, I will upload this code here in a minute. And now go ahead. You can ask your off-topic question. I'm just going to go full screen for a second, so that way I can also work on this at the same time. What's my favorite movie? This is a weird one. It's probably not one you've heard of before. It's called In Bruges, and I'll type it in chat. It's the same writer-director who did 3 Billboards Outside of Ebbing, Missouri. And I also think 3 Billboards Outside of Ebbing, Missouri is amazing as well. But yeah, In Bruges, it's weird because it starts as like you think it's this action comedy movie, and it ends up being one of like the darkest, like what is it? What is redemption? Does redemption exist? how, what is human guilt, um, and it's really really dark and a great exploration of humanity, but it also is. Doesn't that have Colin Farrell? Yes, it does, and I want to be very clear. I have what happens if your Wi-Fi cuts off during the exam? My house is being worked on. My Wi-Fi just cut off for most of this lecture. Unfortunately, there's nothing I can do. What I will say is do your best to make sure it doesn't. If you believe that that would therefore be safer to maybe ask a neighbor to use their Wi-Fi, then I would try to take that step. There's nothing we can do if you lose a Wi-Fi connection. We can't. I mean, Colab actually does not have the tools for us to extend the duration of the exam for a single student, and because we can't verify it, we're just going to have to say do the best to make sure your Wi-Fi is stable. Yeah. Colin Farrell is in it. Colin Farrell is not a good actor, or so I thought. And I will say that Farrell ruined True Detective Season 2 because his American accent was horrible. Colin Farrell cannot do an American accent. Please stop trying to do it. Will Ferrell greater than Colin Farrell? I can accept those terms. But that said, Colin Farrell is amazing in Bruges, but that's because he's playing an Irishman and he's Irish, so that solves a lot of problems. Um, all right, I gotta run. Yeah, no, he's absolutely amazing in Bruges, and I've not seen any other movie with Colin Farrell. I'm like, wow, Colin Farrell's great in that movie, but in Bruges, my God, he's amazing. I mean, he's absolutely amazing. Code from Lecture on Colab. It will be here in 5 minutes. What year do you typically take this class? I generally either this is generally either second semester first year, or I need to see Lobster. It's on Netflix. I need to watch that. I haven't had time. I should note that since the class has gone online, I've had less time, not more. Taking stuff online does not speed things up. It slows it down considerably. I need to see the Lobster. I've heard it's weird AF, and I love weird movies. All right, take care.